Welcome to S Chemistry. I'm your instructor Dr. Suhas Gaudi. I will be teaching BSc 5th semester Physical Chemistry course on Elementary Quantum Mechanics. Here is the outline. In this lecture we are going to see postulates of quantum mechanics. So quantum mechanics, the formulation of quantum mechanical or wave mechanical for the wave mechanical treatment of the structure of atom rests upon a few postulates. So postulates in there are six postulates are there, or in some books there are five postulates are there, but overall content inside these five or six postulates are same. So here I'm going to describe for a system moving in one dimension, say the x coordinates are stated below. So here we are going to discuss only in one dimension, that is x, only x coordinate. So this is the first postulate. So the state of quantum mechanical system or microsystem is completely specified by function psi x t that depends on the position coordinates of the particle and on time. So quantum mechanical system is only for the microsystem, that is for electron, uh, atom or molecules. So and that is if you know the psi function, which is specified like the function of position and the time, that is like a trajectory, kind of trajectory. So the function, this function called the wave function or a state function, has an important property that psi star, which is a function of x and t into psi is a function of x and t into dx, is the probability that the particle lies in the volume element dx located at x at time t. So this product will always give the probability of finding particle between the volume dx. So mathematically it represented in this way. So if you integrate dx of psi star into psi equal to 1, that will always be equal to 1 because it is a normalized function. So where psi star is the complex conjugate of psi formed by replacing I with minus I. Wherever it occurs, the function psi, so in the function psi. So here I value, I is nothing but your under root minus 1. Now, second postulate. So, to every observable in classical mechanics, there corresponds a linear Hermitian operator in quantum mechanics. So, as we know, the classical mechanics, so there are few some observables are there. So, for every observable, there is corresponds to similar Hermitian operator will be there in quantum mechanics. So as we know the classical mechanics, there are position coordinates like position, momentum, like that. So there will be always corresponding Hermitian operator. So the more general definition of Hermitian operator is given by, so we have to integrate minus infinity to plus infinity with respect to dx, that is psi I star into observable a cap into psi j. So this has to always equal to uh, integration of minus infinity to plus infinity. So dx psi I in bracket a star a cap will operate on psi j function, that is into uh, bracket close of a star. So where psi I and psi j are the wave function representing the physical state of the quantum system, such as a particle, an atom, or a molecules. So now we will see the postulate second table the quantum mechanical operator correspond to the observable, that is in classical mechanics, are the constructed by writing the classical expression in terms of variables and converting the expression to the operator. Now we will see postulate 2 table. So here in first column I have given the classical variables. In second column, that is quantum mechanical operator, which is corresponds to classical variable, and third row column is about operator, and fourth column is related to the what we have to do operation on the psi function. So first example of classical variable is, that is x, that is the position. So in quantum mechanical operator we denoted by x cap, and the operator is x. So the operation we have to do, that is a multiplication by x. The second classical observable is momentum, that is px in one dimension. So in quantum mechanical operator we denote as a p cap x, and the operation we do, that is I minus I h cross d by dt, del by del t. So the operation we have to do is taking derivation with respect to x and multiplying by minus I h cross. Now the third observable is your uh, x square, that is your position square. So the corresponding quantum mechanical is x cap square, and the corresponding operator is x square. So the operation is multiplication by x square. Px square into quantum mechanical operator p cap x square. So the operator we have to take is minus h cross del square by del x square. So taking second derivation with respect to x and multiplying by h cross square. So here you can take t. So the classical variable t here, that is a time. The quantum mechanical operator is t cap, and the operator is actually is t. So we have to multiply by t to the psi function. The last but not the least, that is E, that is the total energy, and the quantum mechanical operator is E cap. So the operator is I h cross del by del t. So the taking derivation with respect to t and multiplying by h cross. So here everywhere is only single derivative, that is single differential equation. That is because of our system we consider as a only one dimensional system. Now we are going to see postulate 3. So in any measurement of the observable associated with operator a cap, the only value that will ever be observed are eigenvalue a. So it's a only measurement of the observable. So A is your observable that you have to measure the any psi function. So corresponding the whatever the yield will get, that is your eigenvalue A. So which satisfy the eigen equation. So generally an operator will have a set of eigenfunction and eigenvalues. So and we indicate this by writing. So A operator A cap apply on psi n function, we get um, this is eigen function, we get that is equal to a n into psi n. So here the measurement of the observable yields the eigenvalue, that is a n. Now we will see postulate number 4. If a system is in state described by a normalized wave function psi, then the average value of the observable corresponding to A is given by, that is here this open in bracket close, open and close bracket A equal to integration of minus infinity to plus infinity, psi star a cap psi dt. So where psi are the normalized wave function representing the physical state. So here psi is the normalized wave function, then the average value of the observable corresponding to A is given by. So here psi function is normalized wave function. Then the only we can calculate the average value of the observable. Now we will see postulate fifth. So the wave function or a state function of a system evolves in time according to the time dependent Schrodinger equation. So every wave function or a state function uh, system evolves with time. So that time is according to the time dependent Schrodinger equation. So this is the time dependent Schrodinger equation where H is a Hermitian operator. Uh, H, if you apply on psi function, uh, that is a function of x and t, that is equal to I h cross divided into del psi by del t. So here h is the operator and h cap is a Hamiltonian operator of the system. So here we come to the end of the postulates uh, slides. So thank you. See you in next class. Till then, happy learning.